Hello and welcome to Blockchain for Developers. My name is Akash. I will be teaching you an intro to blockchain, Bitcoin, and Ethereum mechanics. So we're going to be going over why I learned this, the intro to blockchain, Ethereum in depth, and if we have extra time, maybe some applications of Ethereum and general applications of blockchain. So expect from us a review of any important blockchain fundamentals concepts. We're going to cover most of them in this lecture, but after that, we may only touch a little bit upon those concepts. You're expected to know blockchain fundamentals for sure after this lecture. We're going to have some technical in-depth talks that can go as far down as like protocol code. Like these protocols can be kind of difficult to understand, and will slow down as the course like moves into more deep zones, because that's when even me and Nick start to reach our edge of knowledge. So we're really going to be sharing with you cutting edge stuff in this course. We're going to have some pretty rewarding homework assignments that are all programming based, and maybe some readings as well. And we're also going to have some group projects. We expect from your dedication. Please treat this as a 2-unit class at minimum, maybe edging on 3, depending on how well you know your fundamentals. We expect attention and your readiness to learn. So attendance and participation is now 30% of the grade. You have one freebie. That is an unexcused absence, basically, that you can just use anytime. After that, any unexcused absences are going to take 10% of the grade, and more than 3 are going to result in an auto fail for sure. If you're stuck coming office hours, you can also post things on Piazza if you have any technical questions or general questions or things in general. You need 61A minimum for this course, and 61B is recommended. So we will be grading on completion, and this decal will require a lot of focus in class on the material especially. So we decided it would be fair to just grade things on completion, because we know that this stuff isn't that easy to do. It's cutting edge, things can break pretty easily. So we'll be as understanding as we can. We also want to make this a fun experience. We don't want to be like me and try to make this a very miserable experience. Yeah, so this lecture is going to be pretty dense. So try to stay focused. Maybe review the slides afterwards if you're unsure about things, and ask questions coming office hours. So I'm the head of design at Blockchain at Berkeley. I build most things design related. I'll build like websites, logos, sponsorship packages. I help people internally with projects and teach this course. I co-founded the initiative in October 2016 with the Bitcoin Association of Berkeley, which was started in 2014. And I'm a third-year EECS major. I was a software engineering intern at 21.co, and I worked there this summer, and I'm kind of working there part-time still. I also went to IC3, which is a boot camp where I worked with some really top tier like Ethereum smart contract guys, as well as some people from Foundation. So there was a lot of interesting presence at that conference, and I'm really glad I went, because I literally just spent 7 days just learning about Ethereum and the in-depth content, and I can't wait to teach it to you guys. Previously worked in John Candy's lab on BidMac, which is a high-performance machine learning library. I was also a passive investor in IOTA and some other cryptocurrencies, so that's where I kind of make some money in this space, I guess. My office hours are going to be 7 to 8 p.m. on Wednesday in the D Lab. It's on the 3rd floor of Barrels in the green room. Can't miss it. This is Nick. I think you heard about him. He's a 3rd-year computer science major. He's an intern at Cisco and Tesloop. He also went to IC3. He got involved in blockchain at Berkeley last semester, and his office hours will be 5 to 7 p.m. on Wednesday in Worcester. If that changes, we'll let you know on Piazza. If it doesn't change, yeah, that'll be his office hours. So this is kind of how we transitioned. We went from Bitcoin Association to Blockchain to Berkeley, and eventually we ended up with this whole structure. We do all kinds of things. We have an executive board which manages the whole organization. We have an advisory board with some VCs and some industry folks and some mentors. We have R&D, which does research, figuring out the feasibility of quantum cryptography and working with professors. We also have events/meetups. There'll be deep dives into Ethereum, which was a pretty popular event during the summer that we had. There's also project teams that work on internal things, which are pretty cool. A bunch of undergraduates and maybe even PhDs and postdocs will come in, just we're gonna project together and kill it. Education, on the other hand, will just focus on teaching. So we have a fundamentals course, we have this course, we have education consulting, which is then we go out to Fortune 500 companies and we teach their executives. We give them like tailored courses to like educate them on the whole like blockchain space very quickly. So it makes sense for them, it makes sense for us. So they pay us a lot of money, and yeah, that's like a cool thing we do. We also have a consulting and development division. We have engineering teams that work with external companies on building proof of concepts on blockchain. So like Microsoft or like IBM or Qualcomm or any other like company that like wants to build like a POC. We go out there, we talk to them, we talk to them about their needs, and we try to make something by the end of the semester that will show them kind of their vision for what blockchain could possibly do. We also do business consulting, so we'll often like just present like ideas and concepts to people and how they can implement blockchain on their end and make it useful. We also do ICO consulting. If you don't know what an ICO is, maybe you shouldn't be in this class, but an ICO is basically an initial coin offering. People raise money using Ethereum tokens that are built on top of Ethereum to like fund their like, I guess, cause. Yeah, so why is this a thing? Like, why is this whole blockchain development a thing? So there's a high demand, there's a low supply of developers. It's why blockchain at Berkeley is successful. It's early, but like this is really cool because it's kind of like the 90s where you have the web revolution, and then you have you even have like the dot-com bubble that comes up. It's kind of arguable that we are in a cryptocurrency bubble because the total market cap of cryptocurrencies is like 150 billion, and that's like a lot. That's crazy. That's worth more than a lot of like big companies. The majority of people, blockchain is just a buzzword, but it's an important one, and I think you'll see why after taking this course. You'll be able to like envision like some really cool ideas, I think, after taking this course and see the applications and what's true, what's not true. You'll be able to call like all the bullshit for sure. Even if blockchain is in the future, you will still learn valuable ideas by working in this space and learning about the material. Like right now, it's basically people are doing ICOs, but the applications of the future of blockchain are intriguing. So this is a very open community. Like we were, a bunch of my friends and I, we were just walking around and we saw a Bitcoin core developer in a diner. We totally denied it was him, but eventually we grew the balls to just like walk in and ask him like, hey, are you Greg Maxwell? And yep, turned out to be him. So yeah, and then he also had like another Bitcoin core developer right across from him. So these guys are like so core to like building this whole like space, and it's crazy how easy it is to just like meet them. You don't see that elsewhere. There's always like, for machine learning, for example, the top guys who are like building things are always like being bombarded with like emails and people who want to talk to them, and it's hard to reach them. But these guys just work in open source projects. They're like, they're just like, cool dudes who just know their stuff, and they don't get super recognized outside of the space. So the space is very niche, but it's also not ridiculously competitive because it's niche. So there's not a lot of people right now that know about this stuff. Not everyone's eyeing it right now. So I mean, now is the time to get in if you want to be the so-called elite of this like whole arena. It's easy to get internships and jobs and make big bank if you know your stuff. Like there's an article released on CoinDesk saying that like blockchain developers are being like offered like 250K like salaries off the bat just for like knowing their stuff like so well and being able to right on the protocol level. This stuff is hard, so I mean it pays off, but once you learn it, you can become an elite in some way. So some blockchain and Berkeley members ended up with internships at companies like Consensus, 21.co, which is me, Block Apps, SAP. There were other companies like Qualcomm as well. Yeah, these companies are all getting involved in blockchain initiatives. So it's a big deal. You should definitely consider like joining the org if you have extra time. But right now I think applications are closed. So if you want to get involved in other ways by attending events, sure, that's definitely a way you can get involved. You can also reach out to us and see if there's something you can do for us. We're always looking for like people to help. So Bab also does education consulting, which I mentioned. It can lend you a lot of money. Yeah, so let's get into blockchain. I think it's time to go back and get technical again and finally do the exciting stuff. So yeah, remember Bitcoin? What does it provide? So it's decentralized, open source, peer-to-peer crash protocol. It provides account and identity management. So there's addresses for every user. And each associated user is essentially going to have some amount of currency. So that currency sits under somebody's address. The service it provides is basically transactions between users. You need to be able to send money to people. That's Bitcoin's like main purpose. Cache, record management. So you need to be able to store redundant information. Like you need to be able to share it as well between people, and you need to be able to keep track of everything. So this is done via like a redundant information store called the blockchain, and it's basically a distributed ledger, which we'll talk about in the next few slides. You need trust as well, which will basically align personal incentives with the goals of the whole network. So the cool thing is that every user has control of their own information, their accounts, and their own privacy. It's very decentralized in that sense. Bitcoin has some problems, but we won't go into that. But ideally, yes, everybody's in control, and it's very decentralized, and it's the perfect crypto anarchist like mechanism for dealing with money. So let's talk about identity. So there's something called a public key and a private key. So in Bitcoin, every single address is essentially a public key at its fundamental core. And basically you have a corresponding private key that will unlock what's under that public key. So say you have like an address, right, your public key, and it has like Bitcoin in it. In order to use that Bitcoin, you need the private key. So public key is then used to like receive, essentially, and a private key is then used to send your transactions from that place, right? Like you're going to hand out your public key in order to say, give me money, and then you're going to use your private key to basically access what's under that public key to send a transaction. So this is like, these things are paired, right? It's key pair. So how does Bitcoin manage identity? So we need to talk about some cryptographic primitives, and one of these important ones is the hash function. A hash function basically produces a fixed size random looking output, which is pretty much like deterministic. It'll call the same thing every time, assuming you put in the same input. And this is called a hash. Okay, so if you look on the right, there's a diagram that shows you a plain text file that goes into a hash function and gives you hash text. Essentially, what you can do with this is you can detect tampering of data by using hash functions without having to go through like the whole file and saying line by line, being like, oh, like this is different, this changed, right? Like you need a quick way to like verify that somebody like changed something. You use a hash, right? You just use a hash because it'll tell you immediately that somebody changed something if you just run it through a function, and you have different outputs from the initial input. So some properties of a hash function: you have collision resistance. A hash function is said to be collision resistant if it's infeasible to find two different input values where the output of those values is the same. So essentially, I cannot find an x and a y where the outputs of those through the hash function are going to generate the same like hash, right? So another property that's important is hiding. Given the output, you cannot find the input of the hash function. And that's also known as pre-image resistance. You don't want people to be able to reverse your hash. And this is because hashing is actually used for passwords. So like when you enter your password on a website, it turns it into a hash, and that hash is then stored in a database on somebody's server, and therefore the server owner cannot see like what's your password, right? Otherwise, if you're storing passwords in plain text, it's extremely dangerous. There's other techniques to secure your passwords on servers, but basically, hashing allows you to hide things. So digital signatures are also very important primitives, which are related to hashing, but let's talk about this. So these are the digital analog to handwritten signatures on paper, essentially. And they are used in generating Bitcoin addresses, and I'll talk about that in the next slide. But let's go over some fundamental properties of this cryptographic primitive. So one thing is that only you can make your signature, and others can only verify that it's valid. So if I sign a message with a secret key, and somebody tries to validate that with my public key, the signature must validate correctly for it to be like a real signature. Another thing is that it needs to be unforgeable. So it needs to be computationally infeasible to try to forge a signature. Otherwise, people are going to just try to hack through all your public keys and then try to basically generate a public key private key pair. And from that, we will essentially lose out on wallets. So if people are hacking wallets, then Bitcoin won't work. So Bitcoin uses ECDSA, which is the elliptic curve digital signature algorithm. I won't go into depth on how this works, but this is a pretty state-of-the-art algorithm that's used in like government-grade security. So basically, for how digital signatures work with Bitcoin, you need to know that digital signature implementations have a key generator function that will take a key size and generate a key pair. So a key pair is basically, as you can recall, it's a public and private key. So I mentioned in the last slide that it was a secret key. That's the private key, and the pub key is the public key. So now Bitcoin address is then actually, yes. So you generate a ECDSA key pair. However, the Bitcoin address is then a hash of that. If you look on the diagram on the right, you can see that there's a lot of processing that goes on. Like, for example, we run the public key through SHA-256, then we run it through RIPEMD, and then we do some other stuff as well, and then we eventually get a Bitcoin address. It's kind of complicated. You don't need to memorize this, but it's good to know that essentially a Bitcoin private key is actually more complicated than just the raw ECDSA key pair. So Bitcoin allows you to create as many addresses as you want, and you can use a new one for every transaction, and there's no like master address when you use a Bitcoin wallet. Like most Bitcoin wallet software, like the Bitcoin address is an abstraction, because wallets will often have special tools to secure you, and we'll talk about how that works and why that is. So can somebody guess your private key? And the answer is not really. Like, it's going to take way too many permutations to do so. So it's like there's 2 to the 160th possible addresses. If you're trying to like run this key generator function for a digital signature, there's no way in hell that somebody's going to be able to overlap with you. So transactions. What makes a transaction valid? So remember that transactions are the backbone of Bitcoin, so these need to be secure. They need to be valid, right? So you need proof of ownership, which is essentially a digital signature. You need available funds, right? You can't just be sending funds that just don't exist in your wallet, and no other transactions can use the same funds. So this might not seem obvious. This seems obvious, right? Like no other transactions can use the same funds, but basically in Bitcoin you spend like Bitcoins and you generate new ones after like spending them, and I'll show you how. So instead of accounts like one might expect for like Bitcoin, like you have a bank account normally, like for like I don't know, Wells Fargo or whatever bank you use. Bitcoin is going to use something called an unspent transaction output model to ensure that funds are only used once. And this is an interesting design decision, but let's go back to transactions at a fundamental level. So transactions map input addresses to output addresses. And in a typical transaction, there's one input, 2 outputs, and it contains the signature of the owner of the funds. So what are these? What does it mean to have like 1 input and 2 outputs, right? Like how are we getting like 1 input? How are we taking 1 input and then turning it into 2 outputs? Like why is that? So we have something called a UTXO, and that's an unspent transaction output. In an accepted transaction in a valid blockchain payment system such as Bitcoin, only the unspent transaction outputs can be used as inputs to a transaction. Okay, so when a transaction takes place, the inputs are deleted, and then the outputs are created as new UTXOs that can then be consumed in future transactions. So UTXOs are basically unspent and then can be used as inputs to new transactions. So here's a diagram, right? Remember that UTXOs are essentially unspent, so you can use them as inputs to transactions. And eventually, like the end of the chain is going to have unspent transaction outputs, right? So there's going to be a bunch of like floating money in people's wallets that are linked to their addresses, and that's basically how UTXOs work. They basically are used as inputs to transaction functions, and they become new outputs. And this is actually how splitting works for Bitcoin, right? Because you can have less than 1 Bitcoin. So remember, in Bitcoin, UTXO is the amount that's transferred to a Bitcoin address along with the digital signature during a transaction. And the received amounts are used individually during a transaction, and new outputs are created. So remember that one goes to the receiver. So for the outputs, like when you use the UTXO as an input, remember that one goes to the receiver, or multiple depending on how it is, but ideally one goes. And then if applicable, if there's remaining leftover amount for the UTXO, there's change output, and that will go to the sender's address. So UTXOs don't always split like evenly, right? Like for example, I can have a 50K like transaction that I received and that's sitting in my wallet. I only want to give someone like say 30K. I need to basically use that as an input to a transaction because that was my initial, that was an output from a previous transaction. So then I can split it and then eventually end up with, I basically put it through an input function and then I eventually end up with remaining UTXO that goes to my address, and the other person gets the UTXO that we sent them in terms of the amount that we decided when spending. So remember that divisibility of Bitcoin happens this way, and the smallest unit is a Satoshi. It's 10 to the negative eighth, so you can send like very small payments, and this allows for like micropayments. So this is what a transaction looks like. It's kind of this JSON-y looking thing, but basically you can have you have the hash of the transaction, you have the data size, you have like a transaction format version, you have like the number of inputs, the number of outputs. You also have a lock time, which is useful for development. You have the size of the transaction, which can vary depending on how many transactions are in there. If you've heard of something called block size, this is like pretty important because you can only fit so many transactions in a block. If you don't understand what I'm saying, don't worry. If you do, yeah, block size is an important thing that's kind of caused divide in the community. So yeah, you have for the inputs, you have the hash of the previous transaction. You also have an input script. We'll talk about what that is. For the outputs, you have an output amount, a signature, and an output script. Again, we'll talk about scripts because transactions have a bit of a catch from the way we taught them, but just remember the UTXO model, which is extremely important. So we have record keeping on the blockchain. How is that done? So we do this using a distributed database, right? So we have people storing money, so we have senders and recipients, and we have the amount that we're basically like keeping track of each time a transaction happens, and we need to store it. So how do we keep track of all this? Basically, we use a blockchain, and that's a distributed database. So this is what it actually looks like. We won't quite build up intuition quite yet for this, but by the end of like this segment, you will definitely understand like how this all comes together. So everybody's the bank in this case. Like everybody keeps a copy of the ledger, and we kind of all can do governance this way. And I'll show you how, because governance is extremely important for this network to work out, right? Like what stops people from, say, producing the wrong ledgers, right? And what puts people in agreement, right? Like what keeps people to having the same ledger? Like how do you make sure they all have the same ledger and remain honest? Like what if these guys all just decide to collude and just print money, and then a new person comes to the network and sees how expensive Bitcoin is? Will they want to participate? Probably not, right? So let's go into something called consensus, which keeps the network in check. By the way, this is going to get much more architecturally focused rather than technically focused. So this is how it kind of works at a high level. So let's have an example where we have one person sends a transaction to multiple people, and basically everybody accepts the valid transactions without any like discussion of sorts. Like there's no disputes. Like Gloria could have like $10 and she can like say, oh, I'm gonna send Parna like 200, and I'm gonna send Philip like 500, and I'm gonna send Max like way more than I have. How do we sure that someone's not cheating if we make decisions alone? So basically, yeah, this is the problem. Like Gloria can perform a double spend attack if she decides to just promise Aparna 10 BTC and Nadir 10 BTC. But the reality is Aparna doesn't know that Gloria has spent that 10 BTC. So Gloria can essentially perform a double spend attack by saying, okay, I'm going to give you 10 BTC, I'm going to give you 10 BTC. But you're not going to know that I won't have that 10 BTC once it goes to someone. So basically, I'll have double spent Bitcoin that I don't have. Now, this is obviously abstracting away like things on the merchant level. The merchant, for example, like Aparna, could probably just be like, until payment received, like I can't like confirm anything. So yeah, like sure, just bear with me for the simple examples. So this is malicious activity. So instead of like siloing decisions, we can't really keep them in check, right? Like this can happen. A double spend could like happen if we don't keep people in check. So then, how do we fix this, right? We can have proposers and voters that decide. Look, we can have proposers where they submit a transaction to everyone else, right? So, for example, Gloria wants to send a transaction to Aparna. She has to announce it to everybody in the network, and the peers will cast votes. And then the transaction only like saves after receiving a certain number of votes. So this keeps everybody in check, right? This makes sure that Gloria is sending the right money, because if she's not, then then she's cheating in the network, and everybody doesn't want that to happen, because if that happens, then the legitimacy of Bitcoin goes away. So if Gloria tries to double spend, if she tries to do what she did last time, sure, it might work for like one person, but like the reality is she will be rejected by observing peers, right? Like once it's spent, it's spent. It will spend one at a time. So whoever gets the money first will get the money first, and then once it's verified, the other transaction will get rejected. So either Nadir or Aparna would get the money depending on who she sent it to first. So peers vote no on Gloria's proposal, and thereby they notice multiple transactions trying to spend the same funds. So Gloria was essentially trying to use UTXOs like twice. So let's review. So identity, we share a public key to transfer Bitcoin, and we use our private key to redeem it. And we sign transactions using our digital signatures under the UTXO model. And remember that the balance of your Bitcoin balance for your wallet is a summation of all unspent transaction outputs that you can redeem. For record keeping, each entity keeps a copy of the blockchain, which is the distributed ledger. And for consensus, peers cast proposals via a proof of work, which we will talk about, inexpensive process to deter double spend attacks. So yeah, I didn't really cover for the proposals, like how people are incentivized to stay honest and how all the incentives will like align. But the coolest thing about Bitcoin is this idea of proof of work, and that's where all the incentives align. But first, I want to cover some mechanics. I want to cover some very fundamental things that you need to know. So first off, how do transactions really work in Bitcoin, right? So output addresses are actually like scripts, and scripts are basically like pieces of code that like do things on the Bitcoin network. So basically, inputs and outputs through scripting allow for the future extensibility of Bitcoin, which is why they did this. So if you want to do like micropayments or something else programmatically, like if you want to use programmable money, like this is how you would do it. So you can think of like transactions as basically using scripts in order to perform like very basic tasks, even at the fundamental core. But if you also want to do more complicated things, you can use scripts. So things to note: signatures prove ownership of a public key, as we went over. The digital signature is crucial for that because you need to be able to redeem your tokens, and you need to be able to sign off on that somehow. So also remember that the Bitcoin address is the hash of your pub key that's generated from the DSA algorithm. So that is important. Like we went over the fact that you have to hash your pub key gets hashed multiple times, and there's a lot of like security measures in reality. So yeah, it's a bunch of hashes. So the transaction is composed of inputs and outputs that specify addresses. Okay, and spending Bitcoin is redeeming previous transaction outputs. So this is incorrect. This amount can be redeemed by a signature from the owner of address X. However, we hash the public key, so you can't just get it from looking at the address, right? The correct way to say it is that this amount can be redeemed by the public key that hashes to address X, plus a signature from the owner of that public key. So this is correct, right? You essentially, all I'm saying is that you can only redeem an amount by having the public key, the signature, and yeah, that's the only way you can redeem your amount. You cannot just redeem it by having the signature and the owner, like knowing the owner of address X, right? You don't have the public key. You only have the hash of the public key when you're looking at an address, or you have much more complicated than just a hash, as we can recall. You have multiple hashes, so it's even harder. So Bitcoin scripting, it's a language called script, actually. Yeah, simplest language name ever. Or you can call it the Bitcoin scripting language. It's stack-based, it has native support for cryptography, and it's not Turing-complete, it has no loops. You don't want to be able to DDoS the network, because if you have loops, it's like pretty hard to stop someone from like running like infinite loops, and that's called the halting problem. We're going to talk about that later on if you don't know what that is. So yeah, this is an example of a script, like in front of you in the center of the slide. So this is actually one of the most simple scripts. This is a pay to pub key hash, and we're going to talk about it. So pay to pub key hash, yeah, you can see that this is kind of like this is basically like an opcode like type scripting language. Like you use this data and you're basically say, look, I'm going to send my coins to the hash of this public key. And this is the simplest type of like transaction function on the Bitcoin blockchain. It's by far the most common case because you literally just sending money is what Bitcoin is. Like that's what you use. So for complicated scripts such as multisig, this can be a problem. So multisig I will explain later. But basically like you need multiple signers in order to like sign off a transaction, and this can be kind of weird for like the sender side if the merchant say has like a wallet that has multiple signatures. So example is like to pay me, write a complicated output script that will allow me to spend multiple signatures. How would the sender like know how to do that? Like, how can you expect like a sender to just be able to write up a script that looks as intimidating as the one in the right hand corner, right? Because in Bitcoin, the senders specify the script. So the solution is to use a pay to script hash for these much more complicated scenarios like multisig. So basically, pay to pub key hash is basically send your coins to the hash of this public key. Pay to script hash says send your coins to the hash of the script. It's basically an abstraction layer. So by sending something to a script, the script takes care of all the complicated things it might need to send to. Like if you want to send to multiple addresses, you want to send to multiple public keys, you want to like split it up, maybe even mix it, something like that. Basically, you send it to your script, and that's like a huge abstraction because you just send it to the hash, and that's how you kind of locate it. That sounds kind of trivial, but this was like a huge thing in Bitcoin, like since inception. Like this, like really changed the game. This made things a lot more secure because you can write very complicated scripts that can essentially secure how you send transactions. So the merchant doesn't burden the customer then with writing a complicated script, and customer shouldn't need to know anything about how the company stores funds. So pay to script hash is the most important improvement, as we said, and the reason is because multi-signature wallets are like functional because of this, and multi-sig basically requires that you need multiple signees required to send a transaction. So you can have you can specify that you need MMN sigs when generating your wallet. So most common is 2 of 3. So basically all this is saying is I need, out of 3 total signees that are given this key, I need at least 2 of them in order to move funds out of my wallet. And this is much more secure because if you think about it, if somebody hacks an exchange, they get your public key and they get one of your signatures. Well, if the other signatures are held elsewhere in another server, that actually adds another layer of abstraction, which makes it much harder for someone to, say, unlock your funds and just drain your money. This is extremely important for security. So another important fundamental concept, the Merkle tree. It's a binary tree of hash pointers. So you see there's blobs of data at the bottom. Then they're hashed together in the parent. This diagram actually is maybe a little more complicated than it should be. Like, you can think of the data just being hashed before it like goes into its parent, right? And then once it does that, the hashes are then concatenated for each child, right? So we take the hash of the data, and then we concatenate we take the hash of these hashes and we bring them up here, and then we take the hash of those hashes and we put them at the root. And once we have all the hashes, we get something called the Merkle root. Once we like hash everything from the bottom up. So Merkle trees allow for proof of membership because all you have to do is just go through. You just need the root, and then you need the intermediate hashes for that piece of data. So you just need the Merkle branch, right? So if I want to know that this data was in the tree, all I need to do is I just need the root, and then I just need these intermediate hashes, right? To fake the proof, though, you would need to find the hash preimage, which is actually just the data. And second preimage resistance meets this qualification. You don't really need to know what that is. Yeah. So Merkle trees, some more information about them is that the transactions for Bitcoin are actually the leaves of the Merkle tree. And they include something called the Coinbase transaction, which includes the reward for miners on Bitcoin, and we'll talk about that and what mining is and what all that means. But why are Merkle trees important? Basically, in Bitcoin, you have a hash chain of blocks, and this makes sure that you cannot like break the previous blocks on the network. Like by having a hash chain, the structure becomes tamper evident, and these blocks are all linked together. So by having all these blocks linked together, it's basically saying, look, like I'm going to take the previous hash and then I'm going to hash it again in the next block. So if you tamper with any of that, right, you're never going to get that same hash again. So tamper evidence is a huge, huge thing for Bitcoin. Another way it's used is it's used in the Merkle tree of transactions. The way, like, this is actually where the real Merkle tree is used, right? So in the hash chain, we only use the Merkle root, right? But for the Merkle root, the Merkle tree then contains all the transactions in the block. So remember that the Merkle tree is always full, and it duplicates the last transaction to fill in any gaps. So another thing that's important is SPV, Simplified Payment Verification. So the Bitcoin blockchain is pretty big. If you just take block headers, it gets a lot smaller. And basically, by taking the block headers, you can confirm the existing work that's done on the blockchain, right? You can already say, like, look, I basically have all the headers. By having all the headers and not all the transaction data and all the other data that's needed, I can basically just go to full nodes on the network and say, look, I have all the headers, all this proof of work has been done before. You can like confirm it if you want to by just confirming that the nonce hashes with the rest of the transactions, and that I'm like a legit person, like trying to just use payments, right? So full nodes will then get the message, right, and then they will basically just wait for this transaction. They will basically like a merchant would just like wait for the transaction to have enough kind of confirmations before delivering any goods on the network. So the full nodes would then like verify what's going on with your light node, and then by doing that, it's very quick, it's very fast, and it already shows that through hashing, you can already show that a bunch of proof of work has already been done, and you have the correct proof of work on your chain, on your local copy of the block headers. So mining. A Bitcoin miner needs to download the entire Bitcoin blockchain. And the reason is because the Bitcoin miner is verifying transactions on the Bitcoin blockchain. Okay, so step 2 is that after you download, you need to it needs to start verifying the validity of these transactions by checking the signatures and confirming the existence of these Bitcoins that are happening in transactions. So then we create a block using the collected valid transactions, and then we find a valid nonce to create the valid block header. We will talk about how that works. This is called the proof of work, and it's involved in the puzzle that secures the network and aligns incentives for everybody. And you hope that your block is accepted by other nodes and that you're not defeated by another block that, say, found the puzzle in time. So mining is like throwing darts at a target while blindfolded, right? There's equal likelihood of hitting any ring. Faster throwers are going to hit more times per second, and the target is within the green ring. Like you have to hit within the green ring to basically to succeed here. If people get better at throwing darts, then the circle needs to get smaller. So this is an interesting analogy for like how mining hardware, like if it gets better over time, like if people all have like the best mining hardware and people are finding more blocks quicker, then eventually the circle will get smaller and it'll basically readjust the difficulty of the network. And this again is to make sure that incentives are aligned in the network. So you can see here the formula for the hash puzzle that we're going to talk about. So there's this puzzle. You basically take the hash of the nonce concatenated with the previous hash of the previous hash of the previous block, right? And then you take the Merkle root of the current block, which basically verifies like all your transactions like very quickly, right? And you need to find a hash that is less than the target. I'll explain what the target is in the next slide, but basically hash puzzles need to be difficult to compute, right? If finding the proof of work requires little work, then like what's the point in this, right? So that's why we blindfolded the dart throwers in the last example. It also needs to have a variable cost. So like there needs to be a way to adjust like this parameter for like the hash puzzle. Like it needs to be able to change as this puzzle like gets more difficult, or sorry, as people get better in the network, it needs to be able to adjust for that, and it needs to be easily verifiable. There should not be like a central authority to verify anything like for the nonces. Any miners should be able to just perform this like puzzle again using the nonce that the person generated, and then therefore confirm that, oh, this person had a nonce concatenated with the previous hash with the Merkle root for this block that was less than the target. So anybody can like verify like that you solved that it's a valid block. So when miners try to compute a block, they pick all the transactions they want to have added in the block plus a Coinbase transaction, and that contains the block reward to their address, and this gives them a reward so that they actually are incentivized to use hardware and electricity in order to mine in the network. Mining is just, remember, it's just verifying transactions by basically doing a proof of work puzzle. So miners may include any transaction they want to form a Merkle tree of transactions, from which we then take the Merkle root of and reference that into the block's header. So for a block to be accepted by the network, it needs to contain only the valid transactions. That means inputs aren't spent, inputs have a valid amount, and valid signatures. So once the Merkle root is validated, the block header is then created. A block header is an 80-byte header belonging to a single block, which is hashed repeatedly to create a proof of work. It contains a version, a hash of the previous block header, a Merkle root, a timestamp in bits, and the nonce, which is incremented with mining. So then we have the mining puzzle. Remember, it's the hash of the nonce with the previous block, the hash of the previous block header, and then the Merkle root. And you solve this by incrementing the nonce, and then you do that until you keep hashing until you get something less than the target. And the difficulty threshold is adjusted every 2016 blocks. And this is referred to n bits in code. And this is responsible for adjusting the target. Okay, so I know that was a lot, but let's talk about Ethereum. Ethereum is this awesome thing. Like, here are all the buzzwords you've probably heard. It's blockchain, it's trustless, it's decentralized apps, smart contracts, it's DAOs, it's Bitcoin 2.0. I'm going to give you like a real overview of like what it actually is, though. Like, these are actually technically true, but I think it's important to know like what this actually means rather than just spouting words. So Ethereum is basically a decentralized platform that's designed to run smart contracts. There's no single point of failure, and it's censorship resistant. It's pretty hard to tamper with the blockchain at all. Another thing is that it's account-based rather than UTXO-based. We'll talk about that. It's a distributed state machine, so the blocks of transactions are modeled as a state transition function, and you're able to keep track of this and go back between states. Ethereum has a native asset called Ether. It's the basis of value in the Ethereum ecosystem. It's only used to really align incentives at the end of the day, but people trade it as well. It's given to miners as the reward for finding blocks, kind of similar to Bitcoin. So Ethereum versus Bitcoin. Ethereum's main focus is being a smart contract platform. It's complex and feature-rich. Includes a Turing-complete scripting language. Remember that Bitcoin is just a decentralized asset / it's basically cash. It's simple and robust, and it has a simple stack-based language with no loops, and it's not Turing-complete. So Ethereum is account-based rather than UTXO-based. It has a Turing-complete scripting language, which is way more powerful than Bitcoin script, and it enables smart contracts. So the Ether asset is not the primary goal here. It's a side effect to align incentives on the smart contract platform, and we'll talk about how that works. Ethereum plans to move to proof of stake, which is another way of doing like the whole mining system. Basically, you can refer to it as virtual mining as a very simple way of looking at it. We won't talk about that in this class, but if you're interested, you can definitely read up on it. We may post readings. But this is going to come very soon in a hybrid form with proof of work. And right now we're on the Homestead release, but soon Metropolis will release. And we'll have to update this course to reflect that. So Bitcoin is going to remain proof of work. Ethereum is still proof of work, but it will move over to proof of stake. Recall that Bitcoin has basically UTXOs, and the user's available balance is the sum of unspent transaction outputs for which they own the private keys for those output addresses. So instead, Ethereum actually uses a different concept, and those are called accounts. So for example, Bob owns private keys to a set of UTXOs, whereas Evan owns private keys to an account for Ethereum. An account has an address, balance, and it can also have code. But wait, there's two types of accounts. So there's externally owned accounts, which are owned by some person, corporation, or whatever. It has an address, an Ether balance, can send transactions, which means it can basically transfer Ether to other accounts or trigger contract code. Remember, like, smart contracts like need to be triggered by like currency in some way. I'll like kind of talk about that a bit. And contract accounts are basically they have an address, they have an Ether balance, they have an associated contract code, they have code execution that is triggered by transactions or messages received by other contracts or other externally owned accounts, and contracts have persistent storage. So persistent storage basically just means it can store variables and stay there. So the state of all accounts is the state of the Ethereum network. The entire Ethereum network has to agree on the current balance, the state, and the contract code of every single account. Yeah, like I said, the Ethereum network is a state transition machine, and every state is kept track of on a blockchain. The Ethereum network is updated with every block, so you can think of a block as a state transition function. The block takes the previous state and produces a new network state, and every node has to agree upon this new network state each time. Each time, like, we put a new block on the blockchain, and there's like new transactions that happen, and etc. There's a new account state every time, right? So remember, in Bitcoin, we store the transactions. In Ethereum, we're going to store account state. So accounts interact with networks, other accounts, other contracts, and they do this using transactions. So the rationale for accounts is that it saves like a lot of space, and it's way more intuitive than UTXOs, because If you think about it, it's way easier to program because you literally just can like subtract from a balance and take that money that you subtracted. Whereas like in Bitcoin, you have to like put together all these UTXOs and then you know, take out the balance from the UTXOs, and then eventually you end up with new UTXOs, and then you have to spend those UTXOs somewhere else and eventually make sure you have the right money. It's kind of confusing. So for Ethereum, Ethereum uses smart contracts. These are kind of the backbone. So smart contracts are executed by the network itself. Network consensus will remove the need for any trusted third party. Nobody can violate like a contract once it's posted. Like the code is kind of law in that sense. No trusted entity can like fudge contract execution, so you can't really mess with it. Like nobody can just like decide, okay, I'm gonna just make this contract execute completely differently, unless they subvert the whole network. Unless they take most of the mining power. If they own the network by having most of the hashing power / mining power, then like they can do that. But that's pretty difficult to do. So smart contracts also allow for secure peer-to-peer agreements that live on the blockchain forever. So if you want to like put funds in escrow, this is a way to do that. You can have agreements with people to do that, and that's pretty cool. It's like actually programmable money that's very easy to program. So contracts in Ethereum are like autonomous agents that live inside the network. They react to the external world when poked by the transactions of other accounts, and they have direct control over an internal ether balance, the internal contract state, and the permanent storage. So Ethereum contracts serve four purposes. They can store and maintain data, which represents something useful to users or other contracts. Like, for example, you can have a token currency or an organization's membership, or even like if you want to make a game contract, for example, you can store the state of the game. You can also manage contract or relationships between untrusted users. So you can do escrow, you can do financial contracts, you can do like legit like programmable contracts, like financially binding contracts on the Ethereum blockchain. You can provide functions to other contracts. You can serve like as a software library / API, which is pretty cool. You charge people for API calls in that sense. And you can do like complex authentication. So remember in Bitcoin we had pay to script hash that allowed you to do have M-event multi-sig access. Similarly here you can do the same thing. You can also do multi-sig. You can also do some combination of the above. You can make a pretty complicated contract if you wanted to. This is what a smart contract looks like. This is the Philip token. Basically, you can instantiate it with some initial supply of tokens, which can then be transferred between different accounts. And remember that the contract is an account and has its own ether balance, address, and storage, and that's where the balance is like taken from. So it's pretty cool. Yeah, this is a very stripped down version, so this is not actually what your code will look like, but this is the simplest like form of it. So EVM, this is basically responsible for running all the code on the network. You need a stack-based virtual machine to do so, like Bitcoin, and EVM is that solution. So basically, this is a Turing-complete like mechanism, and every Ethereum node will run the EVM as part of the block verification procedure. So you can think of the EVM as a state transition mechanism. You basically put in the whole global state of the accounts, and then you have the memory and transaction and message and code and stack and PC counter, or sorry, program counter. And basically, like you then just keep track of the block state and gas for each like function or opcode that happens via the EVM. So some goals for EVM is simplicity. The opcode should be as low level as possible. The opcode should be minimized in terms of number. They should be space efficient. So assembly should be like easy to like send, because imagine like if you scale this network, it can be pretty difficult to send like large scripts of code, and if they don't compile down to EVM opcodes, then it's not really super portable. So determinism is also very important because we'll go into why that is. I mentioned Bitcoin didn't have loops. Ethereum does have loops, so this can be kind of dangerous, and I'll talk about why. But yeah, this needs to be deterministic because people can really do some messy things with the EVM other ways if it's not. And the same input state should always yield the same output state. So yeah, that just means that like there should be like the same amount of things in the network after the fact that things happened when the state changes through the EVM. Like the network, like there shouldn't be like money just generating out of nowhere from this like EVM code that runs. So some specialization things. This is not like super important. Basically, like some cryptography stuff, but also it needs to be able to read block and transaction data and interact with state. And some security properties is that it should be easy to create a gas model for the operations. So the EVM is like hard to exploit or pretty much like not able to be exploited. So here's how it kind of looks. You can have a Solidity contract, which is the language that you write smart contracts in, or you can write it in Viper, which is like a Python-based smart contract. But we're basically going to be doing Solidity because it's way more developed, and Viper is kind of messy right now. But yeah, the EVM code looks like this. It's basically just a bunch of opcode operations that are happening. Nothing too special. So here's an issue. What if our contract has an infinite loop? So if things are looping forever, you can imagine that somebody will end up DDoSing the network. Like this could be very dangerous because by the halting problem, you cannot determine ahead of time whether the contract will ever terminate. So therefore, you can't detect infinite loops. So that's like very dangerous because if important mission critical things are running on the network, you're running like payment systems. You can't have someone like able to just write a smart contract and just run an infinite loop and deploy a bunch of these and just take down the whole network because then $1 billion is just gone. So Ethereum's solution to this is that every contract requires a fuel known as gas, and that's required to fuel the contract's execution. So every opcode that's run when you compile down your high-level smart contracts requires some gas in order to execute. And this is good, because the deterministic property of the EVM will basically know like every operation you're like working on, and by knowing that, you can calculate how much gas it's going to take to do like your whole operation. So every transaction is going to specify the start gas, the maximum quantity of gas it's willing to consume, and the gas price or the fee in Ether it is willing to pay per unit gas. So then we get something known as start gas times the gas price, which is the Ether that's subtracted from the sender's account when you start the transaction. And if the contract successfully executes, the remaining gas is then refunded to the sender. But if the contract execution runs out of gas before it finishes, execution reverts and your stuff is not refunded. So it's kind of not great for your design, but to be honest, it has to be this way because you need to incentivize people to run code on the network. And if people are running code and people didn't pay enough to run the full thing, then you can't have the miners like just lose money by participating in the network because that just kills incentives. So Ethereum could like optimize its user experience here by just basically preventing people from sending these types of transactions, but it hasn't happened yet. So what about the infinite loop? Does that go away? Nope, it's still there, but if you try to DOS the network using infinite loops, you have to pay gas. You have to pay to DDoS the network. So incentives are completely aligned here. Remember, this is like a decentralized computer, so yeah, people are paying for it. Kind of like decentralized AWS in some ways, but not quite as good in terms of user experience yet. So Ethereum is not about optimizing the efficiency of computation, and the parallel processing you do on the network is redundantly parallel. Like people will run the same code multiple times. Like contract executions are redundantly replicated across the nodes, and this is expensive, but it creates an incentive not to use the blockchain for any computations that could be done off-chain. So if you want to do like some very some very deep computations, like if you wanted to do deep learning on the Ethereum network, that's kind of stupid because you would probably have to pay $1 million worth of Ether just to like, you know, do like some training and output like some like result from your model. Yeah. So we can cover some applications, but I think we're out of time. So we're going to move this to the next lecture. And yeah, I will see you guys in class on Friday next week.